All right, this is our solutions to conservation of momentum in explosions. So here we have two lab carts that are at rest on a track. We'll do the blue one here. We'll do the red one here. Oh, they're next to each other to begin with. So the blue cart has a mass of 0.6 kilograms. The red cart has a mass of 0.3 kilograms. And to begin with, the carts are at rest on the track. So this is one thing that I want really to point out on this. When we have a situation where it says things are at rest to begin with, it's telling you that the initial velocity of those objects is 0. So this is the picture representing what's going on before. So we'll have before on one side, we'll have after on the other side. After everything happens, the carts are going to move away from each other because we're going to extend the plunger between them. It's going to shoot them off. And the 0.3 kilogram cart is moving at 1.5 meters per second in that direction. And what we want to do is figure out what's going on with the 0.6 kilogram cart. Now, here's how we're going to do this. I'm going to go through the problem like it says, looking at the total momentum before and the total momentum after, all the little parts. And then I want to just solve it all at once the way I want you to think through the problem. So there'll be two parts to how we go through this one problem. The momentum of the system before the explosion. When we talk about total momentum, P total is always going to be a sum of momentum. So this is telling me to add those momentums together. So P total before this collision is going to be the momentum of the blue car plus the momentum of the red car. So it's going to be the mass of the blue car, 0.6, times the velocity of the blue car, 0, plus the mass of the red car, 0.3, times the velocity, 0. And so the momentum to begin with is 0 kilogram meters per second. And that's okay, because we said the whole thing was at rest beforehand. Now, this next part is the conservation of momentum. The conservation of momentum says the before the system, the before explosion momentum is equal to the after explosion momentum. Conservation of momentum is momentum before equals momentum after. That's what the conservation of momentum says. So if I want the total momentum of the system after the collision, P total afterwards is still going to be that 0 kilogram meters per second. Because the before momentum has to equal the after momentum. That's how it works. So the question is, how can I have 0 momentum afterwards if we have some momentum for this object going forward? Well, we're going to see what happens, and then we'll talk about that question for a little bit. So calculate the momentum of the red cart after the explosion. The momentum of the red cart after the explosion is going to be the mass of the red cart, 0.3 kilograms, after the explosion, times the velocity, 1.5 meters per second, of the red cart after the explosion. So the momentum of the red cart after the explosion comes out to be 0.45 kilogram meters per second. Now, if I want the momentum of the blue cart after the explosion, what we're going to do is say the total momentum after is momentum of the red cart plus momentum of the blue cart after the explosion. We said our total momentum afterwards was 0, and the momentum of the red cart is 0.45. We want the momentum of the blue cart. So what we see here, we'll do it in blue, that makes more sense. The momentum of the blue car must cancel the momentum of the red car. That's the only way I can get 0 total momentum. So if we look at the math on that, we'd have to subtract 0.45 from both sides. The momentum of the blue car ends up being negative 0.45 kilogram meters per second. When that happens, we're going to have negative momentum. That's how it cancels out. Well, negative momentum means we are moving to the left. So if I want the velocity of the blue car after the explosion, I know that the momentum of the blue car is mass of the blue car times the velocity of the blue car. So it's negative 0.45 is equal to 0.6 times the final velocity. Divide both sides by 0.6, and that makes the final velocity of the blue car negative 0.75 meters per second. And again, that negative sign means it's going to go in the backwards direction. Now, here's what we're going to do. We're going to take this same thing and we're going to solve it in a different way. So we've got this same problem, but I want to solve it sort of all at once instead of working through it step by step, because it's going to be helpful. This is more like the things that you have to do. You're not always going to get prompts that lead you to do this thing step by step. And I want to point out the conceptual jumps that we're making to do that. So this is our collision. We have our before side over here. We have our after side over here. And our big idea is that the momentum before is equal to the momentum after. That's our big idea. So to get my momentum before, that's going to be the momentum of object 1 plus the momentum of object 2. And after, it's the momentum of object 1 after the collision plus the momentum of object 2 after the collision. This part up here is my conservation of momentum, setting momentum before equal to momentum after. Now, in order to calculate momentum, the other thing that we have to keep in mind is that any individual momentum is going to be m times v. So for what we have here, we have 0.6 kilograms times 0 meters per second. That's momentum 1. That's what we got from right up here. Plus 0.3 kilograms times 0 meters per second. That's what we have for object 2 beforehand. So that tells me that my momentum beforehand is 0 plus 0. So my initial momentum, my momentum beforehand, is 0 kilogram meters per second. Then we need to look at what's going on afterwards. So for object 1 afterwards, we have 0.6 kilograms times velocity 2. We don't know what that is. That's unknown. Plus the momentum of object 2 afterwards, 0.3 kilograms times 1.5 meters per second. So we're going to have 0.6 times V2 plus, and 3 times 1.5 is plus 0.45 kilogram meters per second. We'll subtract 0.45 from both sides. So that crosses out. I get negative 0.45 is equal to 0.6 times V final. And V final comes out to be negative 0.75 meters per second. It's just what we did before. I just wanted you to see it all at once, all the way through. All right, we have two ice skaters now. We have Susie and we have Brenda, and they're going to push each other apart, and Brenda's going to slide backward with a speed of 1.2. So they start off standing together on a frozen lake. So we have Brenda standing at 224 kilograms. Susie is standing, her mass is 56 kilograms. And since they're both just standing on ice, their velocity is going to be 0. That's our before. For our after, we are told that Brenda is moving backwards with a speed of 3.2 meters per second. We're going to have to make that negative because it's backwards. And we want to know what Susie, at a mass of 56 kilograms, is doing. So Total momentum of the system before. So our momentum before is momentum of Brenda plus the momentum of Susie. So we've got Brenda's mass, 224, times her velocity of 0, plus Susie's mass of 56, times her velocity of 0. That makes my total momentum 0 to begin with. We begin with 0 momentum, and that means we end with 0 momentum. So my momentum after the explosion is going to be momentum of Brenda plus momentum of Susie. And what we're going to do in D, E, and F is just solve for those parts. I already know that the final momentum after the explosion is 0. But if I want Brenda's momentum, that's going to be Brenda's mass, 224, times Brenda's velocity, negative 3.2 meters per second. So Brenda's momentum comes out to be 716.8 kilogram meters per second. But it's negative because she's going backwards. And so now we have negative 716.8 for Brenda's momentum plus Susie's momentum. So we're going to take that equation, total momentum of 0 equals Brenda's momentum, negative 716.8, plus Susie's momentum. And we're going to solve that by adding 716.8 to both sides. We're going to solve that for getting Susie's momentum. And we're going to get positive 716.8. That's going to be Susie's momentum. And if I want her speed, I know that that's going to be mass times velocity. So 716.8 is equal to Susie's mass, 56 kilograms, times Susie's velocity. Divide both sides by 56. And Susie's velocity comes out to be 12.8 meters per second. All right, moving on to our last two. We've got some pirates firing a cannon. We draw a picture of the situation. So to begin with, my two objects are together. We have the cannon with a mass of 360 kilograms, the cannonball with a mass of 12 kilograms. After we fire, the cannon is going to recoil. That means move backwards with a speed of 5.4 meters per second. And the cannonball, mass of 12 kilograms, is going to go forward, but we don't know its speed. We need to make that 5.4 negative. And for this one, we're going to say that we are not moving to begin with, so the initial velocity is 0. So to do this all in one step, that's all we're asking for here, we're going to say that the initial momentum is equal to the final momentum. So the momentum of object 1 plus the momentum of object 2 is equal to momentum of object 1 afterwards plus the momentum of object 2 afterwards. But looking at what's happening here, since both objects are at rest, my initial momentum is going to be 0. And that's going to be equal to the final momentum of object 1, so the mass, 360, times the velocity of negative 5.4, plus the momentum of object 2, 12 times v final. So we get 0 is equal to negative 1944 plus 12 times that final velocity. So we'll add 1944 to both sides. We'll divide both sides by 12. And we get that velocity to be 162 meters per second. That's how we're going to do this problem all at once. Number 4 is the same way. We've got Dennis, who has a mass of 40 kilograms. So we have 40 kilograms. That's going to be Dennis. He's riding on top of his little red wagon, which has a mass of 20 kilograms. And then Dennis is going to jump so that Dennis stops. He has 0 velocity. and we want to know what's going on, which way is our 20 kilogram object going. This is our picture. Oh, and to begin with, they're both moving at 6 meters per second. Each object's moving at 6. So for this, we're going to use conservation of momentum and say that the initial momentum is equal to the final momentum. The initial momentum is the momentum of 1 plus the momentum of 2. The final momentum is the momentum of 1 plus the momentum of 2 afterwards. So we'll say object 2 is the 20 kilogram mass, object 1 is the 40 kilogram mass. To get an individual momentum, we do mass times velocity. So for object 1, that's 40 kilograms times a velocity of 6. For object 2, that's 20 kilograms times a velocity of 6, is equal to the momentum of object 1 afterwards, that's object 1, 40 kilograms times 0, plus the momentum of object 2 afterwards, 20 kilograms times the final velocity, whatever that might be. So in this whole expression, the only thing we don't know is the final velocity. We got 240 plus 120 is equal to 0, that has no momentum, plus 20v. 20v, and we put those together and we get 360 is equal to 20v. We'll divide both sides by 20, and that velocity comes out to be 18 meters per second.